take a look at some examples from chapter 9. So here's a typical example for first part of chapter 9, find the centroid with integration. So in this particular problem, they're asking us to find the x bar of the shaded area given there. So part of a circle, you can see there's an equation for the line, and it goes from 0 to 4 both in the x and the y direction. In this case, decided to pick a horizontal slab. So, right, the length in that particular case is going to be x. The width is going to be dy, right? So that's the area of that rectangle, x dy. What we need, though, because we have dy, we need x expressed and in y's. So you notice if back, I can't go backwards, unfortunately, when I'm doing this, but if you look back at the previous, you'll see that there was an equation for the line. So we can, and it was given to us in terms of x and y. We can solve for x, substitute that in, and we get the 2y to the 1/2 power. Instead of putting the square root, I like to write the 1/2 power because it's just easier when you're doing an integral to do the integral for that. So and you can see I right underneath that, the line underneath that, right, we were given that y equals 1/4 times x squared, and you can see how I solved that for x. So the x bar for that, right, it's going to be dead in the center of the square. So if the whole side is x, right, x bar is going to be half of x. So, right, you can see half of x. Of course, we need that in y's. So we got 2y to the 1/2 times 1/2 y to the 1/2 for the x bar value. So our integration, of course, is going to be x bar dA divided by the integral of dA. And they're both going to go from 0 to 4. How far are we sweeping that thing, right? We're sweeping it, in this case, in the y direction. It's going to go from 0 all the way up to 4. Happens to be 4 in the x direction too, but we're sweeping it in the y direction. Let's plug all those values in, do the integral, and we find that the x bar value is 1.5 meters. So there's typical doing, finding the centroid with integration. So how do we do the table method? If you remember, right, we take and we look at the shapes and we divide the shapes into common shapes and we populate our table with all those particular values. So in this case, we've got 2 rectangles and we want to find the x bar, y bar for the cross-sectional area of the 2 rectangles. In this particular case, it's probably going to be off the shape, right? Remember we said that can happen where it's off the shape if you watch the overview chapter 9 video. So you can see here, I've got my 2 pieces defined. They're both happen to be 6 by 2. I've called one and I've called the other 2, very original, right? So the areas for each are going to be 6 times 2, even though, right, one of them is 2 by 6 and one of them is 6 by 2, depending upon which one you're looking at. So they're both 12, right? So I sum, you can see in this first column, I've summed the areas as 24. So the x bar value, right, if I look at segment 1, the x bar value, it's too wide, so it's going to be at 1, right? The y bar value is going to be in the middle, so it's going to be 3 over from the edge of the rectangle. However, you have to go 2 to get to that 3, right? So it's 5 in that particular case. Y bar values, again, it's in the middle. So if we look at the first one, it's going to be at 3. And if we look at the second one, it's going to be at 1. All right, and then we've got my x bar A, my y bar A, some of those together. Again, remember, these were in inches, so those are going to be cubic inches in those particular cases. So plug those values in, right? So I've got my x bar A's, the sums of those divided by my A's, and I get 3 inches for my x value. And for my y value, I get the y bar A's, sum of those over the sum of the A's, right? The sum of the A and this is the same in both cases, and I get 2. So my x bar, y bar is at 3, 2. Actually, it's going to be right on the edge, right? So it's going to be 3 over, and then 2 up. It's going to be right on the edge in this particular case, not actually off of it. So there's a good example for using the table method. Last is applying the theorems of Pappus and Guldinus. So here is a tank. We're going to find the volume and the surface area of the tank using the theorems of Pappus and Guldinus. And you can see that the values are listed up there. So what we need to do when we find the volume is we are going to divide the shape up into what pieces we could make that we're going to spin around an axis to get the original piece. So hopefully if you look at this, you can see, right, the bottom of the tank is like a rectangle and the top of the tank is like a triangle. And you can see the pieces, right? So if I took that triangle on that rectangle and I spun it around the y-axis as I've shown there, and I spun it around 360 degrees, I'd get back to my original tank. So that's how you do this Pappus and Guldinus. So we plug the values in, right? So the first thing that you have is you have how far you're spinning it in radians, right? 360 degrees is 2 pi radians. And the second part is summing our yi's and ai's. So if we look at piece number 1 there, the rectangle, right? It's 30 by 15 is the area of the rectangle, right? The y bar would be in the center, so it's going to be 7.5 feet away from the y-axis. That's what you'll notice that I have there for the first term. Right, the second term is the triangle on top, right? 1/2 base times height. So you notice it's 15 for the 1/2, right? That's the area for the triangle. And remember that it's always from the bottom. The y bar is 1/3 of the way in. So it's 15 total divided by 3, of course, 5 in that particular case. Plug in all those values and we get the volume from Pappus and Guldinus for that tank of what's listed there, 22.15 times 10 to the 3rd cubic feet. So surface area is, picture if you had to paint the tank. So we're not looking at it anymore as a rectangle and a triangle. We're looking at the sides that we would have to paint to make this thing painting, right? So we would have the straight side that's on the edge, and we've had the slanted roof, right? Those are the pieces we need to paint. So we need the information about those two pieces. So what we need are the length of those lines and the center point of those lines. And how far we need to turn that thing around the axis, again, it's 360 degrees or 2 pi radians. Right? So we've got yi, which is the length, actually yi is the center point, and li is the length. I got them backwards, it looks like down there on the bottom. The first one I got backwards, the second one I don't. Anyways, right, so how far away is that vertical piece? Well, it's 15 feet away and it's 30 feet long, right? That's the 30 times the 15. So now we got the slanted roof, right? The center point of that is, remember the whole base is 15, so the center point of that line is going to be 7.5 feet away from the y-axis. Now we need to know the length of it, right? It's a triangle. So that top piece is the hypotenuse, right? Remember our original triangle? 15 feet was well, it's the bottom side, the way it's drawn here, and 4 feet was the piece on the far left-hand side. That's the second, so that's the length there. Plug in all those values, and we find that the surface area based upon Pappus and Guldinus is 3.56 times 10 to the 3rd square feet. All right, surface area is square feet, and the last one was a volume. So doing something just slightly different here, right? We can use this, in this case, we're trying to find the weight of the wall. So notice instead of the 360 degrees like we did before, this one is going over 50 degrees. So we're going to take a shape, we're going to spin it over 50 degrees, right? We're going to do that to find the volume of the wall. What's not given here, unfortunately, if you can go look up the problem in the textbook, they tell you the density of the material. So what you hopefully see here, and I think I'll show you here when we flip the page, is you've got a rectangle and you've got a triangle. So we're going to find the information about the rectangle and the triangle. We're going to spin it 50 degrees, find the volume of the wall, multiply that by the density, and then we'll have the weight of the wall. Simple as that. So here's how we do that. All right, so you notice shape 1 is my triangle, shape 2 is my rectangle, and you notice how great my scale is there if you take a look at it. So remember the information that I need. I need to find the area, and I need to find the center point. Right, so these were offset, if you'll notice, by the 60 feet from the axis to the start of the shape, right? So the center point for the triangle, right? Remember, that's going to be a third of the way from the big side. So it's 2/3 of the way from the other side, the slanted side in this particular case, right? 60 feet to get to the triangle, and then 2/3 of the 7 feet to get to the that centroid point, right? And the area is going to be, of course, 1/2 the base times the height, right? Shape 2, we need to go the 60 feet, we need to go the 7 feet, and then we need to go halfway across the rectangle. The rectangle is 8, so that's the 4 right there, right? It's a rectangle, so the area is 30 times 8. So you can see all those values in the top formula. When I plugged the values in, and I kind of got a little lazy that I didn't put in that 71 times 240, but the answer at the bottom of 20.8 times 10 to the third cubic feet is the volume of that wall. You'll notice, right, it's 50 degrees. You need it in radians, so I've converted the 50 degrees to radians by dividing by 360 and multiplying by 2 pi, so I get the value of 50 degrees in radians. That's the volume of the wall from Pappas and Godinez, multiplied by the density that was given in the problem, right? Weight equals density times volume. We do that and we find out that this weight weighs 3.12 million pounds. So there you go. There are some examples from chapter 9.